So let's get started on new stuff. This is the part that I really enjoy from here on, the inferential part. And so we are studying inferential statistics next. That's the rest of the semester. Remember, that just means inferring something from the statistic data. Before we can discuss inferences, we need to understand probability and how probabilities work. So we're going to spend the next 2 or 3 classes working with probability theory. And this is elementary probability theory. Right? So the theory behind probability. To find probability of an event using theoretical probability, doing an actual experiment is not necessary. We just use knowledge about the situation, some reasoning, some critical thinking, known formulas, a combination of all of it, to calculate the probability of an event happening. It is written as the ratio of the number of favorable events divided by the number of total possible events. The law of large numbers. As an experiment is repeated over and over and over and over and over, the proportion of times that a given event occurs will approach its probability.
Do you mind going back one time so I can take a picture?
Do I mind? Yes. Will I? That's a whole different question.
Thank you. I'm done.
Sample space contains all possible outcomes of a probability experiment. So I'm going to safely assume that we've all had at least intermediate algebra. I'm pretty sure it's a prereq for this course. Algebra 2. Which means you should be familiar with set theory. Again, elementary set theory. So you should be familiar with sets, unions, intersections. Sample space is a set. Specifically the set of all possible outcomes. You can also think of it in terms of language of set theory. It's your universal set. An event is an outcome or a collection of outcomes from a sample space. Once again, it's a set. And it's always a subset of your sample space. Probability model consists of a sample space along with a probability for each event. If we're dealing with a model where each outcome is equally likely, then the probability of A, number of outcomes in the set A divided by the number of outcomes in the sample space. So it's the size of your event, how many ways your event can occur, divided by the total number of outcomes, the size of your universal set. There are 25 desks in this room, unless I counted wrong. I'm not counting these two, just the student desks. So of those 25, how many are empty? I'm defining empty as there's no one sitting in it. I counted 12. Yeah, I think I missed the one behind you.
I think somebody's sitting here. So
But they're not there
like
right. They're not there right now. So it's 12. And yeah, you're right. I think I missed that one. So there's 26. So the probability of me selecting an empty desk would be 12 over 26, which is 6 over 13. Slightly larger, slightly less than a half. Some characteristics. This one is very important. The probability of an event occurring is between 0 and 1 inclusive. What does this mean? You're taking the second exam. You're asked to calculate a probability. You get a probability of 1.1. You're not getting any credit. Because you should know you made a mistake. It's got to be between 0 and 1. There are 3 different ways we typically represent a probability. Either as a fraction, a decimal, which is the most common, right? And that's where this comes from, decimal between 0 and 1, or as a percent. If it's as a percent, then the probability is going to be between 0 and 100. 0% and 100%. A probability of 0 means the event is impossible. interesting. Theoretically speaking, there is no such thing as an impossible event. This, of course, just is a consequence of the laws of physics. I'm just not sure. I can't think of one. You submitted an answer of 3 for a test question, and the correct answer was 3.14. What's the probability you're correct? 0. That would be an impossible event. A probability of 1 means the event is certain. Here's where you're going to start to see the morbidity in statistics. What's the probability of you dying? 1. You're guaranteed to die. It's a fact of life. An unusual event is one whose probability is small. As a general thumb, we take any probability less than 0.05 to be unusual. Not for a common misconception. Standardized testing. We're all familiar with it. Given a giant book with a bunch of questions, answer choices A through E, usually 5 answer choices. Say on a random question, you decide to pick B as your answer. What is the probability that your answer is correct? 1 in 5, 20%? That is incorrect. That is the misconception. It's either 0 or 1. It either is or it is not correct. The 1 in 5 is the answer to what is the probability of randomly guessing the right answer. Once you've picked it, it's either right or wrong. Right, so if the answer is C, then your probability is 0. If the answer is B, your probability is 1. That is the common misconception. Probabilities refer to random selections. It's all random. Another common misconception. You flip a fair coin 10 times. How many heads do you get?
Say to flip a coin 10 times.
Fair coin 10 times. How many heads do you get?
Maybe like 4.
Should be 5 out of 10.
That's fine.
The answer is you have no idea until you do it.
Right.
You can get anything from 0 to 10. This is where the law of large numbers comes in. as you repeat that experiment over and over and over and over and over, you're going to start to see that the probability of getting heads will approach 50%. So you'll start to see that over large experiments of time, you're averaging 5 each time. But it doesn't mean you will get 5 every single time. If you do, then it's not a fair coin. That would be a rigged coin. Sampling an individual from a population is a probability experiment. Population becomes your sample space. The members of the populations are equally likely outcomes. The experimental probability of an event consists of repeating an actual experiment a large number of times and finding the ratio of the number of outcomes in which a specified event occurs to the total number of trials. Yeah, and this is a very common theme in probability gambling. Audrey has time to play roulette at most 5 times. We're going to keep it simple. At each play, she wins or loses $1. Very simple. Also not how roulette works, but. She begins with $1 and will stop playing before 5 plays if she loses all of her money. Find the number of ways the betting can occur. I forgot period. How many cases will she stop playing before 5 times? How many cases will she leave without any money? Okay. Something else we need to deal with now when we're dealing with probability is the notion of counting. Counting is actually very hard. It's not a simple concept. In fact, there is a branch of mathematics called counting theory. If it gets its own branch, that means it's pretty in-depth. This is a fairly simple problem to count. What we're going to do is we're going to create what's known as a tree diagram. Starting point, she has $1. There are 2 possibilities. She wins or she loses. If she loses, how much money does she have? 0. Which means she's done.
Wait, I thought she had $5 and she got
$1.
oh no.
She either wins or loses.
Okay.
She stops after 5 or runs out of money. She can then win, in which case she'd have how much?
$2.
Again, the 0 has no branches. With the $2, she's going to play again, right? She's only played once. She can either win or lose. If she loses, how much does she have?
$1.
If she wins, how much does she have?
3.
That is now 2 plays. In either scenario, she's playing again. So go with the 1.
So back to 2.
If she loses,
0.
You get
Okay.
0.
She was $2.
she wins, she has 2. With the 3, if she loses,
$2.
I'm going to have 2.
And what is this called again? This method?
This is a tree diagram.
True, I think.
She wins 4. That is 3 plays. That 0 has no branches. She's done. That 2 does, though. She's only played 3 times. Loses, get her, leaves her with 1. Win will leave her with 3. I'm going to extend this to give myself more space. That's there. 3, 2. This 2, win or lose. Win or lose. I should probably go on this way. That's only 4 plays. So in each of those cases, she's playing again. Win or lose. Win or lose. Win or lose. 2, 4, win or lose. Win or lose. Win or lose. That's 5 plays. Tree diagram is done. These are all of the possible outcomes. How many are there?
When you say unrelated, what do you mean?
How many possible outcomes does she have? You're counting too much. An outcome would be a complete end of the branch.
So 5?
You're close, you're missing 2. There's 14. the 2 zeros that terminated it early. There are 14 ways that her night could end.
What do you count? You count the branches?
Every time a branch ends. So you have that very first 0, that's an end, that's a possibility. Then you have that second 0, that's an end, there's your second possibility. And then the 12 on the bottom. Right, so think of those lines as a path. When the path ends, you have nowhere else to go. That is one possibility. So there's one. That was one walk. You could also walk down here, right? And then you could come down this way, there's the end of a branch. There's your second possibility. And you could come down here, here, this way, down to here. There's your third possibility. Right, notice that all the other branch endings are down here. So that'd be 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. The next question. I think it asked, how many cases will she stop before 5? How many? What'd you say?
3.
I see 2. Where'd you get? Where's your third? So what are your 3?
First 0, second 0, third 0.
That would be 5 plays though, wouldn't it? This third 0. All right, 1, 2, 3, 4, 5 plays. She may be leaving with nothing, but she still played 5 times. So there's only 2 of them.
Wait, can you repeat that one more time?
How many ways does she play less than 5 times?
Oh, less than 5.
All right, the first 0 she only played once. That second 0 is what? 1, 2, 3 plays. And then everything down below was 5. And then, in how many cases will she leave without any money?
1, 2, 3.
4.
How when is 3 0?
1, 2, 3, 4.
Okay.
And that was an easy counting problem. I don't think we get into combinations and permutations in this course. tossing a coin and a die. Explicitly express the sample space for this experiment. So let's start with that. You toss a coin. What are your outcomes?
50-50.
What are they? Heads or tails? Let H be heads, let T be tails. You toss a die. What are your outcomes? 1, 2, 3, 4, 5, 6. So our sample space should have 12 outcomes in it. You toss a heads and roll a 1. You toss a heads and roll a 2. Toss a heads, roll a 3. Heads and 4. Heads and 5. Heads and 6. Could do a tails and 1, tails 2, tails 3, tails 4, tails 5, and tails 6. Those are all of the possible outcomes of this experiment. There are 12 of them. A is the event that you get a heads and an even number. B is the event you get a number less than 3. C is the event you get a tails and an odd number. We're going to find 3 probabilities. First, the probability of A or B. So let's first explicitly state all 3 sets, A, B, and C.
That's 1.
So A was heads and even. What are your
Heads.
outcomes?
Heads 2. Heads 4. Heads 6. Tails 2. Oh, that's it.
That's it. B, a number less than 3.
H1, H2, T1, and T2.
And finally, C, tails and odd. I'm now going to explicitly state A union with B. The union of 2 sets is everything that's in one or the other. And then we also want B intersect with C. And so remember, the intersection is everything they have in common, which is just T1.
T1. So B and C means like, okay.
So probability of A union B. How many elements are there in A union B? How many outcomes do we have?
6.
Out of how many total?
12.
It's a 1 in 2 chance. which is a 50% probability. How many events do we have for B intersects C? Out of how many? So that has a 1 in 12 chance of occurring. And finally, probability of D. Out of how many? So 1 in 3.
And that's it?
Huh?
That's it?
That's it. Generally, the hardest part of probability is the counting. Pair of dice is tossed, and the two numbers on the top are recorded. Find the probability of each of the following. So first, I have two ways to do this, actually. I could explicitly list out every element in the sample space. Or I could just worry about the sizes. Before I list everyone out, sample space is going to have how many elements?
Is this something that's in our notes?
This should be common knowledge. And for you nerds out there, I'm referring to standard die, not the D&D die. I think there are other dies out there as well for different games. We're just talking about standard die, 1 through 6. So how many total outcomes are in this experiment? How many outcomes are on the first die?
6.
How many are on the second die?
So it's one.
There's 36 outcomes.
Oh, 6 times 6.
Yep.
Oh,
I'm not listing all 36. That's way too many. I'm going to represent it that way. Size of our sample space S is 36. So we have 36 possible outcomes. Find the probability that the two numbers are equal. So how many ways can the two numbers be equal?
6.
6 ways, right? You roll 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. So that probability is a 1 in 6 chance. the next probability? Sum is 10 or more. So how can we get 10? 6 and 4, that's 2. Okay, 6, 4, 4, 6, they're different. 5, 5, that's 3. So there's 3 for 10. All right. What about 11? You can get a 5 and a 6, which means you can also get a 6 and a 5. So that's now 5 outcomes. What about 12? 6 and 6, that's the only way. You can't roll anything larger than 12. You have 6 outcomes. 6 ways to get a sum greater than or equal to 10. So 1 in 6 chance. Someone that knows a pattern. I don't like this question anymore. How many ways can you get a 5 on the first die? I'm not talking about sum now. I'm just saying now you roll 2 die. How many ways do you? How many outcomes are there where 5 is on the first die? You said 2.
I said 2.
6. 5 on the first die, and then you can have whatever on the second die. And there are 6 outcomes on the second die.
5 on the first.
And so that's a fixed 5. So it's essentially how many ways can you roll the second die? 6 of them. All 1 and 6. This. How many ways can you roll a 5? It's on either die. You said 12. How'd you get 12?
There's 6 possibilities in the first die and then 6 in the second.
You double counted.
Do I really?
You counted 5 on both die twice. It's actually 11. Right, because there's only one way to roll 2 5s. By doing the 6 and 6, you counted that way twice. That probability is 11 out of 36. See, counting is hard. determine the probability of each event. So here's what I'm going to do. Just so I don't have to write out the whole statement. So probability for A, an even number appears on the toss of a fair die. So how many even numbers are there? And how many outcomes? And so 1 and 2 chance. Probability at least one tail appears in the toss of 3 fair coins. All right, so you toss 3 fair coins. What are the outcomes? You get 3 heads. You can get 2 heads and 1 tail. You can get 1 head and 2 tails. And then 3 tails. 8. Which is how many there should be. 2 cubed. Right, you have 2 possibilities on the first coin, 2 possibilities on the second, 2 possibilities on the third. 2 times 2 times 2. Out of those, how many contain at least 1 tail? 7 of them.
You said how many?
Have at least 1 tail. So that's 1, 2, or 3. In fact, all but the first one. So that's 7 and 8. A white marble appears in the random drawing of 1 marble from a box containing 4 white, 3 red, and 5 blue. So how many ways can you draw a white marble? 4 ways. Out of how many ways can you draw a marble? 12. Probabilities 1 and 3.
I have a question. So you said how many can you make from a white marble? So basically you're counting the white, red, and blue, and the 1 marble itself to get 4.
How many white marbles are there?
White, marble is 4.
There's 4 of them.
Oh,
It tells you
there's
in the
4.
problem.
Oh, okay.
So how many ways can you draw a white marble? 4 ways,
4 and then,
because there are 4 of them.
okay. And it's 12 marbles in total. Oh, okay.
12. There are 12 total drawings
Oh,
because
so
there are
you
12
got-
marbles.
Got you. Thank you.
So A is just the total number of outcomes.
Hmm?
So A is just the total number of outcomes.
Where's A?
I'm talking about like
The numerator is always the total number. So It's the number of desired outcomes. The denominator is the total number of outcomes.
Oh no, I'm talking about like how you had it before.
When you have had it before.
There was like, oh, that's good. I see.
Talking about this.
Yeah, like you see where you have cost.
This one I just explicitly listed out all of the sets and then counted how many were in each one. Here there was no need to do it because they actually gave you numbers for part C. Does that make sense? No probability section will be complete without considering a deck of playing cards. Single card is drawn from a standard deck of cards. Standard deck is 52, not counting the jokers. Find each of the probabilities. Probability of a king. This is going to require you to have knowledge of playing cards. How many kings are there?
So if you don't know this type of stuff in the exam, what do you do? Because I really don't know how many kings is in a deck of cards.
Well, now you do. Yeah, sadly, all of the books consider this common knowledge.
No.
So die, coin, deck of cards, they consider that common knowledge. So they don't tell you. Other things they will tell you if it's not supposed to be common knowledge. So deck of cards, standard deck of cards has 4 suits. Clubs, spades, hearts, diamonds. Hearts and diamonds are red, clubs and spades are black. Each suit has 13 cards. Ace, 2 through 10, no. Yeah, 10. 2 through 10, and then the 3 face cards, Jack, Queen, and King. So you have 1 in 13 chance of drawing a king. Probability of drawing a face card.
And that's considered a joker?
Jack, Queen, or King.
Oh, Jack, okay.
Each suit has 3 face cards. There are 4 suits, so there are 12 total face cards. So 12 out of 52. Or 3 and 13. And generally speaking, you should simplify your probabilities. When we get to later topics, I won't simplify until the very end. Because there are going to be things where we're going to have to wind up adding probabilities and multiplying probabilities. Oh yeah, this is just the basics. We haven't even scratched the surface.
I didn't get that one. So where did you get the 12 for the face card?
There are 3 face cards in each suit. Jack, Queen, and King. And there are 4 suits total.
Hold on. So I don't know about card. How am I supposed to determine that?
Now you know. That's what I'm doing in class. So I guess this is a good time to point out you may want to look up standard deck of cards before the exam.
Face card.
Because I may not remember to write it out if the test bank doesn't give it to me. So I would look up standard deck of cards. Just Google it.
Face card is
And remember, there are 4 suits. 2 are black, 2 are red. 13 cards in each suit. 3 face cards, ace, and then 2 through 10. And then blackjack, ace is either 1 or 11. Face cards are worth 10. Probability of a red card. There are 2 suits, heart and diamond. Each one has 13, so there's 26 red cards. Half the deck is red, so 1 and 2.
So it's 26 black cards. Too.
Yes. Those are the clubs and the spades.
so red card 26. King 4. Face card 2. Red face card.
There's 6 red face cards.
I better write it down and save myself.
So 3 and 26.
I'm writing this.
There's a really good way to get comfortable with the face cards, and that's play solitaire. Or get comfortable with the deck of cards, play solitaire. You'll learn it real quick.
I'm writing this up, please.
That's how I learned my deck of cards, young solitaire. I mean, hell, if you're just giving out money, I'll take some too.
Go be a ginger, but I don't want to do our school stick.
I don't care. I would charge interest.
I did give her interest,
How much?
$1.
Out of the original loan amount. So what was the percentage of interest? My interest ain't cheap. I do 100% daily. Unless I really don't like it, then 100% secondly. Oh, yeah, here's another one. Billiards. Box contains 15 billiard balls, which are numbered from 1 to 15. We are keeping this simple when we're looking at the numbers. Because there's also 7 solid, 7 striped, and then the black 8.
Wait, what? Oh my.
1 through 7 are solid colors. 9 through 15 are striped, and 8 is the black. And it's the last one to sink. And so typically you pick either solid or stripes, and the goal is you want to sink all of those balls and then sink the 8 ball to win. First one to do that wins.
So, is there any other examples other than something?
That would be given to you, most likely. Because they even said it's numbered 1 to 15, so they're not assuming you know anything about billiard balls. Actually, pool is a really good game for geometry. the geometry in pool is awesome. A lot of angles in trig as well. Love it.
So help me God.
Ball is drawn at random and the number is recorded. So find the probability that it's even. You have 7 evens, right? 2, 4, 6, 8, 10, 12, and 14. And there are 15 balls. So probability 7 and 15.
Hold on. Can I please get that? So you counted like even it to 15?
Yeah, so all the even numbers between 1 and 15.
Okay.
How many are there?
7, you remember?
There's 7. Count them out, right? 2, 4, 6, 8, 10, 12, 14.
Yes, so 15.
See, this, they're throwing more information at you than you need. Right? I didn't have to mention billiard balls. I could have just said, consider numbers 1 through 15. What's the probability of picking an even number? Right, so this is literally just about numbers.
Do we have to divide and get the answer, or we can just keep like this?
If I tell you to keep it as a decimal, then yes. Otherwise, keep it as a fraction.
Okay, so if
There are 3 ways to represent probabilities. A fraction, as a decimal, which is the most common way, or as a percentage.
So if you ask like, okay, you need like 2 or 3 decimal points, so then we have to make.
If I say find the probability to 4 decimal places, then you'd actually do what's 7 over 15, 4 decimals.
And
If it just says what's the probability, you can keep it as 7 over 15. And in fact, I would recommend you do. Because I don't know if 7 over 15 is a nice terminating decimal. Right, for instance, 1/3 doesn't terminate. It's 0.3 going on forever. What's the probability of drawing a ball that's less than 5? 4, 4 and 15. Even and less than 5.
Even less than 5.
2 in
I don't think 7 plus
15. 2 and 15.
No, they said 7 plus 4. I said, how did they get that? But it's wrong, so I don't want to know.
I don't know where 7 plus 4 is coming from.
Yeah, I don't know.
6.
Even or less than 5.
Even.
So 1, 2, 3, 4, less than 5.
So
Then
2. So
6, 8, 10, 12, 14, 9, 9 and 15.
Hmm.
You said 4 less than 5?
Even or less than 5.
So even or less than 5, so we have to count everything?
That satisfies that. So less than 5. You have 1, 2, 3, and 4. They're less than 5.
Now you want to get the even number.
Evens, 2 and 4 you already counted for. Don't double count them.
Then 6,
6,
10,
8,
12.
10, 12, 14, 9.
And what about that one? Even and less than.
That's just 2 and 4.
So 2 and 4. So we don't have to put the furthest only 2 number. Like only
Yes,
2.
because those are the only 2 evens that are less than 5. right? It's not 11 because that would be double counting 2 and 4. In math, or is inclusive, meaning one or the other or both. So what you could do is you could go, okay, how many are less than 5? There's 4. How many evens do you have? 7. Right, so that's 4 and 7, which is 11.
I wasn't thinking.
But now how many are both? That'd be the 2. So you could also do 7/15 plus 4/15 minus 2/15. But we will actually cover that. That is a rule.
So wait, so basically being that you asked for even less than 5, we could have just did the 7 plus that 2 already that was given to us to get the no?
You could do the 7 plus the 4, then minus 2. Right? You could count all of the numbers that are less than 5. There's 4 of them.
Okay.
Count all of your even numbers. There are 7.
7, right?
Now remove all of your duplicates. Those are the
the 2.
even and less than 5. That's the 2.
Okay, thank you.
I didn't get that. Let's do
Hmm?
it. I didn't understand that. We can just do it.
So how many are less than 5? How many numbers are less than 5?
Do 4.
I'm not saying even and less. I'm saying how many numbers are less than 5?
Less than 5. So it's 4.
List them out. What are they?
1, 2, 3, 4.
Now, how many even numbers are there between 1 and 15?
2, 4, 6, 8, 10, 12.
7. And good, you listed them out. Remove the duplicates. So how many did you count twice? 2 and 4. So you remove those 2. So it would be 7 plus 4 is 11. And now removing the ones that you counted twice is minus 2, which gives you the 9.
Okay.
That's the other way you could do it.
Yeah, I like that.
Good.
Trying to.
Let's take 10. We'll come back at 7:25. And if you came in late, come up to pick up your test.
You are right.
You did good.
What was it?
No, I'm doing rough all of my tests.
Oh,
Oh, that's not bad.
So that's your.
You beat it. I forgot to send back, but I'm gonna take that.
Oh wait, you said
Gina.
Janelle Patel, right?
Yeah.
it is 3.
83.
You can keep it.
Probably did not see.
Yeah, the grade's on the back.
You get from this.
You just.
I gotta do it.
Go ahead.
I'm glad you let me do you. Maybe you have seen this, right? So I did this. And Let it work. I won't leave it like that. Give it.
I do not have my solution with me. I don't fully remember which it was. Shoot me a message reminding me to reload this in first grade. The what? I don't like the quizzes.
All right.
I'm going to be doing something. I just don't know what yet.
Okay. Thank you.
Keep doing them for now,
Okay.
but I am going to be doing something.
That's. Yeah, this one's
The what?
Doesn't we have to offer our shirts?
Oh, yeah, I haven't done the roster yet. So I have a huge backlog of grading,
Oh.
so I just haven't done the roster yet.
And for the quiz, I can answer tomorrow inspection or I can today. I know that this due.
So it was due at 6 p.m. So I can
Yeah.
I can talk about it after class if you want to stay.
Oh, okay. Because that's so weird. I'm using that material, whatever is they
I also
provide.
I'm
don't
looking at the
understand.
quizzes.
I use the calculator and I see that I'm not using any other stuff. I'm using your material and I'm like, how come it's like this?
Looking at the quizzes.
I'll talk with you after that.
Do not look at these quizzes.
Why didn't
I was gonna say something
you-
too.
you
I
not
did the
give-
one today, and I was like,
I do not.
You not give us some paper quiz like introductory
Read it all
phrasing
back.
is online.
The course
Right.
was written for me.
I said,
Like,
yeah.
but
I
I
said,
said,
Yeah, that-
paper.
everything-
I'm gonna wait. I'll talk to him.
That's so
But
weird.
if it
That's
is,
why I said.
Because
My calculator did mine, so I
like
know
use
that's
a
no
calculator
way.
to put that answer and still is.
I'm like, I did everything right.
Yeah, the calculator gave me.
I'm like, look,
I will be doing something with them.
Did I
Like, there's no way that that's.
Alright.
What do you have to put in there?
I'm glad I'm not the only one. That's it. I'm glad I'm not the only one.
I'll probably go back through them when I get a chance and look at the ones that are auto graded as well.
Because even when I did the homework, it's the same thing, like it marked me wrong for a lot of stuff, but it wasn't wrong, it matched their answers, but it wasn't how they weighed it out.
If it's not, if
Okay, I got one.
Okay, okay, everybody.
Are there any manual graded ones? Are there any questions that need to be manually graded? Are there any ones that I have to grade on that quiz that aren't auto graded?
They're all
They
still
auto
online.
graded,
Then
but how,
that's auto graded.
if it's not how
But
they
it's like, that's so
ordered
weird. That-
It says like R equals, and you're supposed to fill in a number. I wrote R equals and
Yeah.
then another,
So
so
it
maybe
made
that's
it
what's
get
making
That's
it
wrong,
wrong.
yeah.
No, I didn't put that one still is wrong.
That's why I wasn't doing it like that, I couldn't figure it out.
It was
That is
so
not how I do
simple.
mine.
don't know why they
Like-
I make my online quizzes as they
So she's
questions.
like,
Sir,
So I actually have to go in.
they give us this material online the book. We using this, I use that one, I use a calculator as per that direction, and still it's pop up like so.
I think
weird.
it's because we don't write it how the computer writes it, so it marks
It's-
it
you think
wrong.
like if you round
If it
numbers
doesn't- so with
differently or
the-
you don't put
Yeah.
With
it-
fill in the blanks, it has to be exactly as the solution that's put into the.
Yeah, so if you round differently
Computer.
or if you add an extra number, it's just marked.
So if it's not, and it's not just that,
Oh, but it's
syntax as
also-
well. If
you can't
if
put
I
the
accidentally, if I would have accidentally put a space in the answer
Oh.
and you don't, it's gonna be marked wrong.
But how do you
Also,
know
like,
you
I can't
put a
write
space
R
in the
squared.
answer? It's
That's-
like instruction in there.
And it's
I mean,
not mine.
it tells you to put a
So-
comma, but it doesn't tell you about
Yeah.
space.
I'm gonna
Right.
Okay, wow.
I'm gonna do something.
Yeah.
I'm gonna
Because
do
when
something.
when I looked at my grade, I said,
Don't worry about
I
the
looked
quiz.
at
I saw the test grade, I was like, alright, cool, and I went back
That
to
is
the
auto
like,
grade, is
Right.
being part
I
of
was
the
like,
weird number.
my average just dropped like a
Don't-
whole grade.
And
Don't
how
worry
do you
about
know
the quizzes.
like,
Keep doing them.
what
Don't worry
they're
about the
asking?
grades. I'm gonna
It's
do
no
something.
instruction on top, so like, oh, what is this?
when is the project gonna be graded?
As soon as I get a chance to grade it. Right now, tests are my most important thing.
You can just do it like this.
I've got 2 more tests to do.
With your other class or with us you're referring to?
No, with other classes.
Okay.
And then I actually have a test coming in this week too, so I'm gonna have 3 for it soon.
What about the project?
That's
That's
what I
what
just
I'm
added.
Oh, okay.
So did you grade the first project?
That's kind of low on my docket. Tests and quizzes are number 1 and 2 priorities.
And I know next week, not next week, but the following week, in 2 more weeks, what is that? It wouldn't show, it was like Martin Purple though. Is that like another quiz that's due?
Well,
In 2 more weeks?
I take it points.
Oh, quiz, okay, thank you.
The quiz just went up, or quiz will go up tonight.
No, like in 2 more weeks, it showed like it was something else due.
The 23rd, some project 2 is due.
Oh, project.
Yeah, there was a second project. The second project went up today.
Yeah, okay, yeah, I seen that. It wouldn't
Exam
show.
2, we have same thing as open book here, all exams. Like, how many exams you have? 3, 2, 3?
3 tests.
So all is open book?
All open notes.
Don't give us timer.
I love it.
Because for here I finished almost here, but 3% I didn't get the chance. I finished at 4. So don't give us timer. It's like the number going so fast.
Puts on
We're
the
getting
pressure.
nervous too fast.
Puts on that pressure.
Yeah, that is super pressure.
Timer's there for me. Because I'm not good at paying attention to time. And it's also there because otherwise I get everyone always asking how much time do we have left. So I just put it up there and go.
Is project 2 consist of us doing another mini lab?
Minitab, yeah.
Oh my lord.
Oh, speaking of which, apparently Minitab changed, so her video's wrong. I have to fix that link.
It is different now.
Yeah, they updated Minitab and now it's different. She sent me a new video link. I just have to
That's
upload it.
what I said the last time.
I had to use Excel for the quiz today because anytime is different. Excel, it all got the same answers, but
I just like mine.
Which means she has to update her. They have to update the master course.
yeah. Well, the mini stuff too.
Show me why I don't make technology videos because it changes.
I just gave up.
Every time it updates, it's now,
Oh,
the
yeah.
video's completely useless.
And when I was also using Minitab, like the columns, like the Excel part, it went in like become large. I took a picture of how it looked. Like, I don't know, it was giving me trouble. I'm about to show you.
I don't like Minitab either.
Yeah, I don't like it.
What percentage do you have to have to pass this course?
Define pass.
Go to the next. And I have to retake.
Define not have to retake.
What is
That
the
you get the
passing
credit for
grade?
the course.
Like a C or
Again,
better.
define what you mean by that.
Over 60 or something like that? 60 or above?
Because 60 or above counts as passing here and you get credit. However,
Depends on your program.
that credit doesn't transfer.
The nursing.
So if you needed to transfer for your program, you need 70 or above.
Like for nursing, you have to get C or above.
I'll take it.
C's that get degrees.
That's right.
For a master's? Yeah, that's not a good attitude to have.
But now, I'm good.
No, it's not a good attitude to have.
As long as you don't take those quizzes. As long as that one's not standing.
Compound event. Any event formed by combining 2 or more events. So we've already looked at some compound events. Contingency table is a table showing the distribution of one variable in rows and another in columns. Don't know how often I'll be using contingency tables.
So you won't be using compounds of it?
Oh no, I will. Compound events. We've already been working with them, by the way. It's just now we're going to study those more in depth. So one of the most useful ways of visualizing sets is what's known as a Venn diagram. and it's really odd. Something as simple as a Venn diagram was actually very difficult to create graphically on a computer. So A union B. Again, it's everything that is in A or B.
Is that considered a contingency table?
No, this is not a contingency table.
Okay.
This is a Venn diagram.
Oh, Venn diagram.
A intersect with B. Everything they have in common. Here is our first special formula for probabilities. For any two events, A and B, probability of A union B is the probability of A plus the probability of B minus the probability of A intersect with B. All right, so this is kind of how we finished. Right, you count how many are in A, you count how many are in B, and you remove the duplicates. How many did you count twice? You remove those. This can be extended too, by the way, too, if you have 3 events. Right. Rearranging this, you can get the probability of A intersecting with B as probability of A plus probability of B minus the probability of A union B.
I mean, do all of this to make it like I get it without the second part of it. So it's just adding on.
What do you mean the second part?
So I get the first part, but then when they put all the rest behind the equal sign, it started to make it confusing.
Well, that's the formula.
I get it.
This is where the theory is. That's where the theory comes in. Man, you're more of an applied person, not theoretical.
So if the second one's, it's like the A intersect, what is A union?
Everything in both.
Okay, so
Mutually exclusive events. 2 events are mutually exclusive if the probability of A intersect with B is 0. Another way of saying it, 2 events are mutually exclusive if they have nothing in common. Their intersection is empty. So mutually exclusive, well, actually that's kind of, I was going to say sunny and raining, but actually that can't happen. Crap. Can't use dead or dead in the water either. Good old Schrodinger. Schrödinger's cat. He's dead and alive in every other state until you make an observation.
I'm sorry, not to like backtrack. Can you just explain that little U thing in the middle and the down again? I know you probably.
Union and intersection
Okay, thank
for
you.
sets. So they're operations.
Thank you.
Be good mutually exclusive. Door being open and door being closed. Those are mutually exclusive. It can't be both open and closed. So that'd be mutually exclusive. Can't think of any other ones off the top of my head.
Walking and running.
Define walking, define running.
That's
That's up for subjectivity.
what I figured.
Because some would say jogging would be both walking and running. You're kind of somewhere in between. Can't think of any really good ones. Dead and Alive is really good, but again, according to quantum mechanics, and you don't know that until you make an observation. So, the complement. If A is any event, the complement of A is the event that A does not occur. I believe the notation of the book is A to the C. That's what I would try to stick with.
You said A and C?
A to the C.
Oh,
So
A
it's
to
that
the
first one up there.
Okay.
That's not the one we typically use, though. We typically use A bar. So I may slip up and do A bar. If I do, just understand that means the complement. This is where the idea of universal set becomes necessary. It's the gray shade, that's A complement.
What's gray?
Oh, I forgot this bulb is crap. That pink shade that should be gray.
Okay, thank you.
It's what's shaded. So everything outside the circle. So when you draw a Venn diagram, you also need what's known as the universal set, and that's the rectangle that the circles are in. That would be considered your universe.
And the shade is what again? One more time? The term?
That is the complement of A.
Complement? Okay. Thank you.
So we're given events A and B, where the probability of A is 0.6, probability of B is 0.3, probability of A intersect with B is 0.2. First, find the probability that A does not occur. That is, we're looking for the probability of A complement. So let's think about this logically. A intersected with A complement. What is the probability of that? It's 0, right? You can't have both A occur and not occur. What is the probability of A union with A complement? 1. It's guaranteed. Either A occurs or it doesn't occur. One of those two is guaranteed to happen. So, since A intersects with A complement, they're mutually exclusive. That would be 0. So 1 would have to equal the sum of the individual probabilities, right? So the probability of A occurring plus the probability of A complement occurring has to be 1. What's the probability of A? I'm about to be upset. I'm about to be upset. So what's the probability of A? I'm just asking for A right now.
0.6.
It's 0.6. So 0.6 plus what is 1? It's the same as 1 minus 0.6. Which is what? What is it? Probability that A does not occur is 0.4. Probability that B does not occur.
0.3.
What was it? It's 0.7.
How y'all get that?
How we got that?
Has to be 1 minus probability of B.
Okay. So the one is constant?
That one has to be for complements.
Well,
Only because B and B complement are mutually exclusive. And it's guaranteed that one of them occurs, right? Either B occurs or B does not occur. It has to be one of those two.
complements only.
Probability of A union B. Because you double counted it. So probability of A plus probability of B minus probability that both occur.
Oh, so you just put it on together.
Just 0.7. See, that formula is important. And then neither A nor B. This is where logic
What
comes
do
in as
that
well.
mean?
How do you get 0.1?
So neither A or B, like 0.6 minus 0.3, and then minus 0.2. What is that wrong? Or is it 0.3? Is that 0.6 minus 0.2?
It's 0.3.
Okay, so then
Is 0.3, but I don't think for the reason that you were saying. Neither A nor B means what?
Relate.
So neither A nor B occurs would mean what? A doesn't occur and B doesn't occur, right? And this is why I said this is where you kind of need a little bit of logic.
So when the
So if A doesn't occur and B doesn't occur,
yeah, it should be.
that means A or B doesn't occur. So complement of A intersected with complement of B is the same as the complement of A union B. This is why I like the bar notation better. So let me just draw that. So it's 1 minus the probability of A union with B. We just found that. What was it?
Point 0.3. Oh,
So that's 0.3. You want to keep that handy.
so when the operation is facing down, that means less.
Hmm?
Like that operation song.
No, that's intersection.
Yeah.
So that's called a cap when it's upside down. That means intersection.
Thank you.
When it's facing up, we call it a cup, and that means a union. We have a weighted die. This weighted die gives us this probability distribution. Consider 4 events. A is an even number. B is 2, 3, 4, 5. C is less than 3. And D is greater than 7. We want to find, how many probabilities is that? 7 probabilities. Using this probability distribution. Now, that's nice because most of the work is done for us. The hardest part was the probabilities.
So for when I say 8 even numbers, it's like 2, 4, 6 basically.
That's what even, yep. These events, are they mutually exclusive? So when I say events, I mean the outcome.
Oh.
Are the outcomes mutually exclusive? Yes. You can't roll both a 2 and a 5, right? Oh, that's going to make life a little bit easier. So probability of A occurring. So the probability of rolling an even number. Well, that would be probability of rolling a 2 plus the probability of rolling a 4 plus the probability of rolling a 6. And we don't have to worry about double counting because they're mutually exclusive. So that is the formula.
So how do you know when they're mutually exclusive?
Think about rolling a die.
Oh, because it's only 6.
Can you roll a 2 and a 3?
No, okay.
Right? Can you roll a 2 and a 4? Can you roll 2 numbers at once on a single die? No. So all those outcomes are mutually exclusive. They cannot happen together.
So if it was a double, then no.
If there's 2 die, the event for each die is still mutually exclusive.
Okay.
What is the probability of rolling a 2? Heard it. Probability of rolling a 4.
1.1.
And then the probability of rolling a 6 was
0.2.
so the probability is 0.6. I guess it would be a good idea to actually make sure that this works. 1 and 3 is 4, 2 and 6, 1 is 7, 1 is 8, 2 is 10. Perfect. They sum up to 1. That's nice. If they didn't sum up to 1, we'd be in trouble. All right, so there's the probability of rolling an even number with this weighted die. Now we want the probability of rolling a 2, 3, 4, or 5. But we know what the probability of 2 was, which is 0.3. What's the probability of rolling a 3?
0.2.
And we know 0.4. What is the probability of rolling a 5?
0.1.
Sum them up. So 0.7 is that probability.
one the easiest one?
That's because they gave the probabilities on it.
Yeah.
That's why I said they did the hard part for you.
Yeah, it's just the easiest.
What we're gonna do on the test?
Again, those formulas are useful, aren't they? So that's why theoretical math is better than applied math. What was event C? Less than 3. So what does it mean to roll less than 3? 1 or a 2. And again, that's mutually exclusive. So it would just be that, wouldn't it? What's the probability of rolling a 1?
0.1. 0.3. 4.
So the probability of rolling something less than 3 is 0.4. What's the probability of rolling greater than 7? 0. It's impossible.
There's no 7.
Next up was A and B. So A was even numbers. B was 2, 3, 4, 5. What is their intersection?
2. Would it be 2 and 4?
2 or 4. So 0.4. Right. A union with C. So even number or less than 3. So what are those outcomes?
1 and 2? Wait,
Even or less than 3.
One and two.
it's just 2.
Every number is just 2.
It's just 2, yeah. Because it said even
Even
and less
just
than
2.
3. Or is it 1?
Did I say intersect? I said union.
So 1.2?
So you roll even or less than 3. How can you roll an even or a less than 3? What is it? So I agree 1, 2.
1, 2, and 2.
2, 2.
1 and 2 less than 3. So that takes care of that.
So it'll just be 1, 1?
Even so it'd be 4, 2, 4 and 6.
1, 2, 4, 6.
Yes, you smart, bro.
Oh, because it's 4.
Or less than, right? It's even or less than 3. 1, 2 less than 3. 2 is even, already counted for it, so don't count it again. 4, 6 are even. Now, what was it? It was B or no, A or C. Yeah, right. 1, 2, 4, 6. Probability of 1, 0.2. Probability of 2 is 0.3. 4 is 0.1, 6 is 0.2. Sum them up. 0.7. B intersected with C.
So it'll be, so it's like 2, 3, 4, 5. With 2,
Just 2.
yeah.
It's just 0.3. Probabilities are easy.
Because you know it, so it's easier for you.
The probabilities are easy. It's the counting that's hard.
He said we have to multiply. I ain't saying
So we're not quite done with probabilities yet. What are we looking at next week? Next week is conditional probabilities, and we start studying random variables next week.
So exciting.
Is it for? Yeah, conditional probabilities and random variables. We start studying it, so we learn what a random variable is, and then we look at discrete random variables.
Did you notice that during class, you're the only one in here that look happy?
It's because I haven't taught stat forever.
You're the only one in here that's smiling.
Stat is a blessing. I guess that's a problem, isn't it? Well, if I don't make you cry, then I don't do my job right.
Professor, today's creed, I'm confused about today's
Quiz.
the one we just Professor, the quiz we submitted today.
Don't worry about the quizzes. I'm going to do something with them. I'm going to go back and do something with them.
I'm feeling bad right now.
I know that.
We were talking about it.
Because I don't know. I want the video sent to the rec and I don't know how to do it now.
I got it.
He says he's audibly.
So I am going to go back and look through all the quizzes.
You still want it?
I would recommend you use the next half hour to start the second project. I mean, you can, but that'd be wasting half hour free to start the second project.